I'm honored to introduce our keynote speaker for today, Dr. Michael Greaves. Dr. Greaves is an internationally renowned expert in product lifecycle management, or PLM, and originated the concept of the digital twin. His focus is on virtual product development, engineering systems and complex systems, manufacturing, especially additive manufacturing, and operational sustainment. Dr. Greaves wrote the seminal books on PLM, Product Lifecycle Management, and Virtually Perfect, driving innovative and lean products through PLM. He has consulted and done research at world-renowned organizations, including NASA, Boeing, Newport News Shipbuilding, and General Motors. Dr. Greaves, the floor is yours.
Good day, and good morning, everybody. And let me share my screen. And Nia, did I do that successfully?
We see your slides.
Good, thank you. So good morning, and I'd have to first say I never knew that digital twin would become a verb, but I'm very pleased to see that. Nia's been right, is that this has been a huge of interest and has dramatically increased. I did a podcast in 2018, and I did a Google search and came up with about 1 million hits. Recently, I came up with 9 million hits, and today, while I looked, it's 12.5 million hits. So there's a huge interest in digital twin, and certainly the future of digital twinning has implications for all kinds of things, including national security. I'd like to first start off by showing the conceptual digital twin that was introduced at an SME management forum, and then later at the University of Michigan when we were setting up a PLM consortium in 2002. And it hasn't changed. I just might note that at that point in time, the idea of having sub-virtual spaces wasn't well known. While we have one real space for the physical world, the ability of the virtual world to have multiple virtual spaces where we can do work was a new concept. But it didn't even have a name at that point in time. It simply was the conceptual ideal for product lifecycle management. And so the focus here was this idea of the model that I came up with when I was at NASA, and courtesy of NASA had much better graphics. And I dropped off the sub-virtual spaces because by that time we kind of understood that. But and it goes to the point where I'm not a fan of definitions, because I liken them to the blind men and the elephant, that depending on what part of the elephant they describe is going to be a definition. And I think you need to look at an entire model. And in this particular model, there are sort of three main components: the physical space, the physical environment, and the physical products and processes in them that we've had since time immemorial. The new thing that we came up with in terms of being able to have digital capability is this idea of a virtual space, a virtual environment with virtual products. And then the connections between the two, we take data from the physical space and we send it over to the virtual space. And then we use that information to do all kinds of things. And the focus here is this idea that in the 20th century and before, we were stuck in virtual space, and that's the only thing we had. We want to move work activity in the 21st century into this idea of virtual spaces. And the reason we want to do that is that we can substitute information for wasted physical resources. And I'd like to spend a minute kind of talking about that, because I think that this is basically fundamental to understanding why the digital twin has taken off. And that is my premise, that information is a substitute for tasks, wasted time, energy, and material. And people focus on what is information. And regarding that concept of information, there was a quote earlier on, is one thing is certain from the literature: there is no consensus, no clarity, but plenty of confusion. But I think the focus needs to be, what does information do? And if I take any task, and most of human existence is goal-seeking activity with minimum physical resources. So we want to minimize physical resources. So I can take that task and I can divide it into two portions. The green portion is the minimal amount of physical resources I need. So if I was omniscient and omnipotent, this is what I'd want to do. Everything above that is wasted resources. And because we live in a capitalistic society, we can cost those resources, time, energy, and material, and understand what we're doing. Now, these sorts of tasks are, designing a product to meet specific requirements, manufacturing a product to specifications, maintaining a product to operational standards. So these are the kinds of tasks. We also have tasks that we do every day, such as getting 3 kids to and from after-school sports events, minimizing our resource usage. The idea about information, and this is fundamental, is that information is a replacement, not for the physical resources that we need to do the tasks, but for the informational inefficiencies. Now, here I'm showing that information is replacing all the information inefficiencies, and that's the ideal, but that's never going to happen. The issue with information is that we don't have a unit of measurement for information. Some people have said that we need to call it wits and not bits, but the idea is that information, the proxy for that cost can be the cost of hardware, software, people's time in processing information, and so we can kind of get to that. Where this whole thing works is the idea that we basically are going to use information when the cost of information is going to be less than the cost of wasted resources. And given the fact that as I'll talk about and it was already mentioned about the computing capability, this keeps getting better and better as physical resources get more expensive and virtual resources or digital resources get less expensive. I want to point out that since this is a national intelligence thing, that there is the idea of negative information, and that is information that basically causes you to waste resources in adversarial situations. And I think one of the best examples of that is Operation Mincemeat during World War II, where we convinced the Nazis that the Allies were going into Greece and not Sicily. And so we really have to worry about that. The problem is that you never necessarily know what's negative information prior to using it, but we need to be concerned about that as we look at the use of information, and especially in a national intelligence operation. We can basically waste an infinite amount of resources using this negative information when we should be not paying attention to it. So with respect to computing capability, I'd like to kind of talk about the fact that this is what's enabling modeling and simulation and AI and digital twins. And those of you who are familiar with Moore's Law, which probably should be everybody nowadays, will understand that this is a semi-log graph that basically starts off in the early 70s, and it's Moore's Law, which was really not a law, but a prediction by Gordon Moore about the number of transistors on a chip, which is a proxy for computing, would increase, would double every 18 months. And so we started off, at 2K chips, and we recently passed 80 billion chips in a NVIDIA chip fairly recently. I had the opportunity of being involved with the first supercomputer, which was the ELIAC 4 in the 70s, and we had 25 megaflops worth of computing capability. Today, you can get an Xbox that has 12 teraflops and is a fraction of the size. And if you look at Oak Ridge National Labs and their Frontier system, it's 1.1 exaflops, which means we've increased capability 1 trillion times during this period of time, which is pretty amazing. I don't think that chart does it justice as a log chart. If you look at it in a normalized chart, you can see that we have pretty much reached the inflection point, and we're going pretty straight up in terms of computing capability. And if Moore's Law continues to increase the way it is, my predictions are by 2030, we're going to have 7 trillion transistors on a chip or equivalent. I mean, this is multi-core and all kinds of other things, which is 128 times increase. and by 2040, 885 trillion, or a 16,000 times increase. So we have a huge amount of computing capability coming on stream. And I think that this is going to allow us to do the sorts of things that we may think is science fiction today, but is certainly going to be available to us. And it's certainly going to enable the digital twin capabilities that I'm going to talk about in the future here. So I'd like to talk about sort of the digital twin model, and the scope and scale of tangible things has been dramatically increasing in pretty much all areas. And I had always thought that there could be intangible things I'll talk about in a second, but I stuck to tangible things because people can get an understanding of that. So in automotive, in locomotives, in power generation, airplanes, ships, oil facilities, we basically see digital twins. And these are things that I've seen actual papers talking about or examples from industry about using digital twins. And so it still has the same three things: the physical space, physical environment, and physical products, the digital environment and the digital products, and then the connection between the two. We're seeing it in smart cities, in Earth digital twins, and even in the medicine field in terms of patients and pharmaceuticals. But I need to point out that when we're talking about people, my belief is that it involves their physiological capabilities, not how they think. I think that's the one thing that we won't be able to have a computer do, and that is duplicate human intelligence. But in terms of physiology, their functions and things like that, we certainly can do that sorts of things. We are now moving into intangible things, which are ideas that if we can visualize something, we can basically be able to create a digital twin of that particular thing. So if I look at the kinds of things that we're doing in the intangible area, logistics, the process industry, which is there no specific granular product, but certainly the process part. I've seen papers on economic systems, manufacturing processes, and then below there, this thing I call supply nets, which is the idea that there's a corollary for supply chains, which are physical movement of product, with supply net, which is moving information about the product in place. And clearly, supply chains, as we'll talk about later, has a national intelligence issue. So we're seeing things on the tangible side. We're seeing things in intangible where we can basically use visualization. So I want to talk a few minutes about digital twin types, because if you look at the little graphic here, my focus has always been the fact that we were moving from a functional operation with siloed information into a product-centric one where we're going to populate and consume information about the entire life cycle. And I divide the life cycle into create, build, operate, sustain, and dispose. And I'll talk about sort of the first three. The disposal one doesn't get a lot of play, comes in and out depending on government regulation. But there are three types of digital twins depending on where I am in the product life cycle. So my first type of digital twin is what I call the prototypical digital twin, or the digital twin prototype. And as you can kind of see from the graphic, is that it takes form over time. We start off with a vague idea, and we basically start to deliver by the end a physical product that basically comes out of it. And the idea is we really want to make all our mistakes in this particular area. We want to design the product virtually, test the product virtually, manufacture the product virtually, and support the product virtually. And only when we get it all right do we want to go out and move expensive physical atoms. And these are all the products that can be made. So these are the products and the variants. When we start to make products, and I'm talking about complex products, and in this particular case, this is an F-35, we want to capture the digital twin instance of the actual thing we made. We no longer have a tolerance, we have an exact measurement. We no longer have an idea in assembly, we got a serial number. And so we want to capture that information, that data, and create a digital twin instance that we're going to keep connected with its particular physical thing throughout its entire life. And these are all the individual products that are made. Again, it's complex products. As I'm fond of saying, we need one for an F-35. We certainly don't need one for a paperclip. But if we can basically have use cases that's going to allow us to use that information, we want to create a digital twin instance, because if we don't start off with how the product was made, we're going to have a hard time maintaining that product throughout its life. The third type is what I call the digital twin aggregate. And the digital twin aggregate is this idea of having the information about the digital twin and being able to use that information to collect the causation, but I'm good with correlation about how it's going to perform. And so these are all the products that have been made. The digital twin gets a lot of attention, but the physical twin is pretty important because this is IoT driven. And what we need to do is, one of the key links are collecting the data from the physical world. So we've had smart products for a while, as long as we've had electronics, and that means sensing, translating that sense into something that we understand physically. We compare it to what we want it to happen, and then we react in some fashion, either having the equipment react or we do react. Smart connected products, which are digital twins, is we communicate that information, we assess it, and we respond in some fashion. So when airbag going off, we want to basically get that information and send immediately emergency crews. But the thing that these physical twins need to do is protecting. They need to be paranoid as hell because of the fact that once we open communications up, we can have adversarial issues. So these are the physical twins, and this is IoT driven, and this is important as my digital twin is. There are two categories of needs that we have for these physical twins. We need to capture the physical entity itself and capture that information, how fast the plane is flying, what its fuel usage is, whether it's having fracture issues. But the environment, the weather, the adversarial reactions to that, and even what the pilot does, is what we also need to sense. So we need two categories of IoT sensing for physical twins. And again, I can't emphasize the cybersecurity aspect of this enough. I just want to spend a second because and it started off the fact that the digital twin only occurs when there's a physical counterpart. When something rolls off the assembly line, that's the only time we have a digital twin. And if you heard from Nia's definition, it's as soon as we intend to have a product, we have a digital twin. So the twin metaphor only requires duality and similarity, not timeline simultaneity. And sometimes people use the metaphor of a human twins, which is not applicable, because quite frankly, the digital twin framework should cover the entire product lifecycle, as I'm showing from that little diagram below. The DT actually exists prior to the digital twin physical one, and it always has. It just has a different name in some cases, and it's not semantics. I'm a big believer, in fact, my dissertation was on the topic, is how we talk about things is how we think about things. So it's not just a semantics issue. We basically have to have the thinking of that. And again, go back to my little graphics. We really want to populate and consume the information from a product-centric perspective. And if different areas have their own information, we're going to go back to a siloed version, and that causes a lot of problems. A big problem with manufacturing has been engineering designs that what they want the product, they throw it over the wall to manufacturing and say, go build it. And you go back and forth as that occurs. We need to have that, in essence, in a consistent fashion. So it regresses to being functionally siloed if we don't have a digital twin right from the intent to build a product. And that sort of is a key thing. And finally, I think it's conceptually an elegant piecemeal to have the idea that we have something before we have a physical product, and then only then we have a digital twin. So I've seen this early on in terms of the digital twin material. I see this less and less, but periodically there is a group that basically makes a claim that there is no digital twin until something rolls off the assembly line. And I think a huge value of the digital twin is in the development phase, where we can make all the mistakes that we want and it doesn't cost us anything, as opposed to making them into the physical product, where mistakes there can be not only costly, but a huge safety issue. So there's kind of three things that we're focused on here in terms of what the digital twin does. And I call them interrogative, predictive, and learning. And so interrogative is simply the ability of being connected to their physical counterpart, and no matter where you are in the world, have the information about it. You don't, in the past, you used to have to be in physical proximity with something in order to be able to have information about it. Today, through the digital twin, we can interrogate the digital twin. So in this particular case, how much fuel does this tank have? What is its position? How many rounds has it fired? One of the huge advantages of digital twins is the predictive capability. So the ability of aggregating a population of products and being able then to look at, when I see these sensor readings, I basically can predict this kind of failure or anomaly that's going to occur. So the air inlet is partially clogged and needs cleaning. Engine bearing F61 will fail in the next 40 hours. So the ability of being able to predict from an aggregate using, in some cases, Bayesian probabilities allow us to get to condition-based maintenance and get away from periodic maintenance, which means we're going to fix things too late or sometimes fix things way too early. Finally, the learning aspect. So if we have this population out of that based on tank experience, we want to throttle back X miles per hour when incline in Y degrees in order to prevent tread slippage. So learning from previous products so that every new product doesn't have to go through the same learning curve is going to be extremely important. So I want to take you through the life cycle with the digital twin because I think that's pretty important in understanding how the digital twin impacts the entire life cycle of the product. And again, we start off in the create phase where we have the virtual space and we have the digital twin before we have the physical entity, and we want to make all the mistakes there over on the right-hand side, and we want to develop that information so we can trade that off for wasted information. But at the end, we have to have a physical product in a physical environment. And so physical reality trumps virtual reality all day long. If we're thinking we're doing a flying carpet, it's, even though we may tweak it to get it to fly in virtual space, it's never going to fly in physical space. So we actually have to come up with a physical product. But it's not enough to do that. We also have to come up with a means of production of that physical product. So it's not enough to have, great drawings and engineering designs and modeling and simulation. We need to basically have the manufacturing capabilities to realize that particular product. And so this is the create phase where we use the digital product prototype. And again, it's not only coming up with a physical product and modeling and simulating it so we get its behavior, we've got to be able to make that. When we get into the build phase, and we're making multiple ones of those, we have probably the most complicated part of the digital twin environment. And that is we ideally want to have the means of production and the instructions for creating, in essence, taking raw material in one end and a finished product out the other end, and be able to pass that on to those virtual machines and have them send that information to the physical ones. We obviously want to realize the physical product on the left-hand side, but at the same time, we want to, in essence, create its digital twin instance to basically be able to have the beginning of that physically manufactured product that is specific to that particular product and be able to start to track that out through its life. So we want the as-builds, and we want to be able to maintain those as-builds through its entire existence. So we're going to use the prototypical digital twin, which basically has a lot of the information that we need, but then a digital twin instance that we create at that particular time is going to be used throughout the entire life cycle. We want to sustain that particular product, and we want to basically, throughout its life, as we operate and sustain it, be able to maintain that information and be able to do the things that I talked about in terms of interrogate the product, predict what it's going to perform, and be able to have it learn from previous versions. And so we use the digital twin prototype, the digital twin instance, and the digital twin aggregate. One of the opportunities here, though, is to feed back from the operation to in essence the design of that. So too often I see multiple generations of products having the same problem. Why? Because nobody told the engineers that it didn't work the way they had assumed it was going to work. So we want to feed that information back and learn from how the product actually works in its real environment to understand that particular thing. So that connection is really important in terms of it. And we don't do a very good job at having in the past, but with a digital twin, that should be something that now allows us to do that. So I want to spend a few minutes talking about the fact that the digital twin is time unconstrained. And what I mean by that is, in the physical world, we're stuck in the time that we're at. At time Tx, that's all the environment that we're going to have access to. Now, the first use of that is what I call replication. So we replicate that in the digital world with its digital twin. So we capture that information. But now we have the ability of we're not constrained by time in the virtual world. We can go backwards in time, and there are some issues with that, but we can certainly capture state changes and even turn the time arrow backwards in modeling and simulation. And we can do forensics to find out, what happened at a particular point in time that caused this anomaly to occur, or this problem to occur with the product. Where I think we have a huge opportunity is going forward in time with what I call front-running simulation, which I view as a crystal ball into the future. And the ability at every time X to basically run a new simulation of having the exact information of where I'm at with that particular product, but being able to predict what's going to occur in the future. I'll talk about this a little bit later, but this is the idea of that every time X, I'm going to predict out to look into the future to see what's going to happen. We kind of do that today when we're driving, but this is an ability of looking at the sensoring reading that have coming in and being able to predict kind of future outcomes. So the digital twin, has a great opportunity in that it's unconstrained by the time limits that we have in the physical world. So how are we getting here? So I want to kind of show you the physical to virtual evolution that's been taking place. So previously we were pretty much, except for our own mental faculties, in a physical world 100%. As soon as we had an idea about a new product, we basically had to put it into physical form, either sketch it out, do a description of it, do blueprints, do something in order to make it physical. So pre-1980s, we had blueprints and physical prototypes, and we were pretty much only involved in the create phase of the product lifecycle. In the 1980s to 2000s, we then started to move things into the digital arena. We had 2D CAD, and remember, it was called computer-aided design because the issue was we weren't creating a digital model we could use. We were really having the ability of being able to create physical blueprints in a fast way, but we still had physical prototypes. In the 2000s was a huge era for us in terms of moving into the digital arena. We had 3D CAD, and that was a quantum leap in terms of being able to have a model in 3 dimensions that we could examine. We went to digital mock-up units instead of prototypes, and I had an event in the early 2000s where the automotive business had dramatically decreased the amount of physical prototypes they had to build because they were using digital mock-up units. We went to digital manufacturing, which is the ability of being able to predict better performance, and the idea of lean manufacturing came about, and then certainly modeling simulation with computer-aided engineering. The 2010s, the digital twin comes about, and while it was introduced in the early 2000s, it really needed the amount of computing capability we started to generate in the mid 2010s in order to really think about digital twins as a reality. We had 3D CAD, digital mock-up units, virtual reality. We had digital manufacturing, factory replication, where we could capture that stuff off the factory floor. We had multi-domain CAE, and then IoT comes into play and additive manufacturing. In the 2020s, we're starting to see intelligent digital twins, AI. Those of you who have used the ChatGPT are seeing kind of implications of that. 3D CAD, again, the virtual reality, the factory replication, multi-dimensional CAE, and then IoT, augmented reality, being able to in essence overlay the virtual onto the physical and additive manufacturing. My predictions for the 2030 is basically we're going to move much more into the virtual area with intelligent digital twins. I think that additive manufacturing is a huge opportunity in basically custom material or multi-mode material to do AM, and I think that the digital twin is an enablement of AM for production. I'll have time to talk about that today, but I think it's a fascinating opportunity to reshore some of our manufacturing if we can get to that particular era. I'd like to talk a little bit about the digital twin evolution. And the digital twin evolution is this idea that we're going to basically evolve over time with digital twins. And the idea here is that if I look at the information evolution, the amount of information that I have, and then the physical to virtual maturity, my predictions is that we're going to see some impressive movement in terms of moving into this virtual space using information. So physical to virtual maturity is going to increase, and we're going to have this idea of information evolution. So phase zero was the traditional way. And as I said before, as soon as we had an idea of a product, we had to basically make it into physical form. We had to do blueprints. We had to do sketches. We had to do physical prototypes. Excuse me. So this is the idea of since time immemorial, we were stuck in the physical world. If we had an idea, we had a very difficult time sharing that idea with other people unless we put it into physical form. And so since time immemorial, this is the idea that we had. And we did a fairly good job at it. I mean, we in essence put a man on the moon using sort of traditional capabilities. The 2000s were what I call the formational or transitional period. We started to move pretty dramatically into the physical world, into the virtual world from the physical world. And again, I will say that 3D CAD was a huge quantum leap in terms of the opportunity of having the information from the physical world in the virtual world. IoT starts to come along about that time. Digital twin, as I showed, what was proposed as an idea of being able to have a replication of the physical world into the virtual world. And so the early 2000s were a lot of the technologies that came about in terms of being able to allow us to have this idea of a virtual digital world that allowed us to reflect the physical world and then model and simulate from that position into being able to create things. What I'll claim is that today what we're in is the conceptual or ad hoc. We have digital twins, but a huge application of that is we really kind of do the work of being able to create the virtual environment, and we have to be the intermediary between collecting that data and being able to organize it in the virtual digital world. And then the information comes back to us to use. And so while that's not particularly an issue, one of the big problems is that if it's ad hoc, it means that we are basically stuck with the idea of having to have different digital twins, and there's not an interoperability to them. So, for example, if I take an airplane, and I have a digital twin of the fuel tank, the airplane, and the engine, if I fill up the fuel tank, while it reflects the fact that that fuel tank has filled up, it also will increase the weight of the airplane. And so this idea of the fact that these things all need to work together, the different digital twins, is something that we pull together ourselves at the moment, and is an ad hoc basis. Saw a great application of this in terms of an oil field in the Middle East, but they spent huge amounts of money to basically be able to brute force take the different aspects of that oil field, the wells, the pipes, and the refineries, and be able to create a digital twin of it. Very expensive, although it paid off for them immensely in terms of hundreds of millions of dollars of cost versus billions of dollars of savings. It is something that not every organization can do, which is, I think, where we're going, is this idea of digital twin platforms. And we're starting to see that. Sometimes they're called the metaverse, although I'm a little iffy on the exact application of that at times and what it actually does. But I think directionally, that's kind of where we're going, where we have digital twin platforms that allow us to, in essence, have digital twins working together to in essence, replicate what's happening in the physical world. Where I think we're going is this idea of front-running simulation in intelligent digital twin platforms, where we basically have this sort of crystal ball into the future that allows us to do a much better job of predicting possible outcomes and being able to handle them before they occur. One of the things I might mention that is the difference between this and Industry 4.0 is Industry 4.0 had started off as the idea of being able to decrease the amount of time between a failure and remediation. Digital twin is the opportunity to not have or having a failure, because you're predicting things that are happening and you're going out and fixing them before they occur. So this is my idea of the digital twin evolution. And it certainly happened faster than I had anticipated, but we still have a lot of work to do, as I'll talk about at the end of this. So I wanted to spend a few minutes on artificial intelligence. And so my idea of artificial intelligence is a spectrum from the smart calculator to the T1000, those of you who are Terminator fans. And so the idea of it, that is on this expert system, on a spectrum from expert systems to singularity, which I don't think is going to occur, but that's my personal position. And again, intelligence is this idea of goal seeking while minimizing scarce resources. And as I talked about, information is a replacement for wasting resources and doing that goal seeking. But we have dramatically different hardware than computers, even though it certainly looks like that they can mimic us reasonably well. But my perspective is that we don't need a replacement for humans. We have plenty of humans. That we are going to need an assistant to humans to make us better, which I call acute availability versus human replacements. So this is sort of my perspective of AI, and I think that we're starting to see, in fact, those of you who use ChatGPT probably recognize it as a nice addition, but they don't think it's going to replace the way you think about things. So my perspective is that we're going to an intelligent digital twin. And this is the idea that says that not only do we have one opportunity in the virtual space, we have multiple opportunities, and we're going to look at various things, such as we can capture lessons learned. In the physical world, something happens and we move on, and there is maybe forensic evidence of it, but in the virtual world, we can capture the exact state of things and be able to then go back and review that. This idea of acute availability, giving us better information about what's going on so that we can make better decisions. This idea of sense making, helping us get out of boxes that we basically put around things to try to make sense. A couple of examples of that have been the Air France disaster out of Brazil, where pilots kept doing the wrong thing because they had gotten into a box about what was going on. So bias prevention, I mean, the two big biases that humans have is confirmation bias, which I sort of alluded to, is only looking at things that confirm what they thought was happening. And then humans are way too optimistic. Ask anybody who has been involved with projects, the prediction of the project, even though people have never been able to meet their deadlines, is that they're going to meet the deadline for the new project. This idea of front-running simulation multi-scenario is with probabilities, I think it is coming about. And then simply decision-making and support is going to be a big opportunity for us. So what are the impediments? And I think there are, a fair amount of those that are occurring that we need to worry about. And two things that are kind of the two sides of a coin are the hype potential and then decision maker knowledge deficiency. So seeing all kinds of overhypes about what digital twins can do, including that digital twins are going to basically be able to predict human behavior, which I don't think is going to occur. And the problem is that the decision makers who are not digital natives for the most part, and older, have not been brought up in this environment, have a knowledge deficiency of what's possible. So the idea that says you're going to go in and propose, a $200 million project for Boil the Ocean digital twin project, I think is a huge problem. I mean, I've been on the board of public companies, and the people who have been on that board don't have the knowledge to basically be able to sort, real projects from projects that are pie in the sky. And so my proposal is you've got to pick projects that are going to basically build up to projects that are going to be low-hanging fruit in order to be able to build trust and understanding. Organization culture and inertia. This is not just a technical problem. I mean, let me just take the testing community who thinks you have to do 10,000 coupons at something in order to be able to assure yourself. Organizational cultural inertia is a big problem. The other thing is information is power. And a lot of people are not going to want to give up their power because they have the information in their organization. So this is a big issue, and I think it's not been very well either researched or understood, that this is a huge issue for digital twin impediments. Use cases, we need to basically develop use cases. We have to create value for these things. If you don't have you say, I'm going to give you a digital twin and it's going to look just like the physical one, but I can't tell you where the value is, it's a waste of time. And so use cases are going to be instrumental in developing digital twins. I mentioned lack of interoperability and integration. I think that's going to be a big issue as we start to see digital twins proliferate. They need to all have commonality where I can basically be able to have this version of digital twins that work together in the physical world. And then the big one is cybersecurity. So in the physical world, we can put something, in a remote location, in a physical security with physical fences around it and armed guards. When we start to open this up into virtual space, the opportunity that I said that we can have instantaneous and simultaneous connection to something no matter where it's in the world is also an Achilles heel of digital twins. And so it's not simply the fact that adversarial people can do bad things with our products. It's just simply them having the information about that product, the data that's coming off of that is an issue. So at the macro level, obviously you can think of the issues of your weapon systems or even innocuous things that adversarial have access to that information. And certainly when we allow it to be actuated remotely, that increases the issue. But one of the big issues is at the micro level. I mean, the world now runs on chips, and there is a project at Bridge that is being done by the DoD, AFRL, specifically to talk about how do we control what's on a chip so that we have a digital twin of it, and we know that the way it's being manufactured and the way it's being designed and being manufactured is such that there isn't adversarial things on that. And then where I actually am scared stiff of it is autonomous emergent behavior, when we talk about having autonomous systems with artificial intelligence. And when we talk about emergent behavior, most emergent behavior in the past has been, we just didn't know that was going to happen. Today, we could have true emergent behavior if systems can basically change their own parameters. And so at a minimum, we have to have a digital twin overwatch capability of everything that we have out there, so that at least we have an ability to intervene when there is a particular problem. So again, I think this is one of the big issues that we need to deal with in terms of the cybersecurity aspect, especially when we're talking about the national intelligence arena. This is particularly key in our addressing this and being able to assure ourselves that we have the most paranoid digital twins and their physical versions out there to prevent adversarial actions against them. I just want to show this slide roughly to talk about, these are digital twin general use cases that I had done a number of years ago. And as you can see, usually, in fact, I can point to papers that basically talk about the value being created with pretty much any of these particular general use cases. But I like to sort of hone in on use cases for national intelligence. And so the idea here is the fact that we have specific use cases that I think are NI focused. In the create phase, we basically have, weapon system development. We got to do a much faster job in terms of digital twins and understanding the weapon systems development. One thing I might point out is that the former Assistant Secretary of the Air Force, Dr. Roper, just announced that he's got a new company, Istari. He's been a big proponent of this idea of developing in his particular case, airframes digitally, and being able to do all the work there. And what I said before is create the product, create the airplane virtually, test it virtually, support it virtually, and only when you get it all right do you actually go out and build something you fly. Seen a paper on battle damage assessment, being able to look at battle damage and predicting that in the development phase. I talked about semiconductor chip development, being able to make sure that there are no adversarial things there. And then mission planning. So basically reality capture, and then integrating all the intelligence around that. In the build stage, I would claim that onshore manufacturing can be enabled by additive manufacturing, semiconductor manufacturing, and then the idea of supply chain net monitoring and assessment, having digital twins of supply nets that basically allows us to know exactly where our products are by having their digital twins be transmitted to us well in advance of getting the physical version, I think is important. I talked about in the usage sustained phase, cybersecurity, disaster prediction and response, the ability of being able to predict what disasters could occur and how they're going to respond. I mean, we're going to hear about smart buildings, the ability of being able to predict how a building will react in an earthquake, obviously is, given the earthquake in Turkey and Syria, would be hugely useful. National infrastructure, predictive maintenance and replacement. I mean, we need to do a much better job there. And then using this for training is going to be a big opportunity. In the disposal phase, monitoring nuclear waste. And so these are just my sort of versions of NI-focused use cases. But again, digital twins have got to be driven by use cases, and they've got to create value. But I think that there's a wealth of opportunity in this particular area to leverage the use of digital twins in being able to do a far better job. And as I've said, we're looking for the replacement of information for wasted physical resources. So this came from last week's from the the National Academy webinar that they had, and this was a panel on digital twins, R&D needs and investment. And so my perspective of research areas are that we need to look at, being able to in essence have a virtual world where ontology, standardization, and a minimum harmonization are basically being defined. I'm a little reluctant to basically say you have to have standardization, because there's a lot of political aspects of that, and it really is tough to sometimes get standardization, and sometimes they don't move. The standards don't move as the advances in technology occurs. Interoperability, I talked about that. We need to have these digital twins of being able to interoperate and be able to use them to build up not only system from components, but system of systems. We have to do a better job in terms of causality, correlation, and uncertainty quantification predictions. And then I think a big opportunity is data physics fusion, being able to use both big data and first principles of physics to do a better job projections. And then, as I mentioned, the cultural area, I think, is a big issue in terms of how do we move the culture today of I need to physically touch it and see it in order to be able to work it. We have digital natives coming into the workforce. I mean, the workforce of today and the future, these people have never not known that they had access to digital capabilities. And so we have to in fact, move it from the social aspect to using it for useful things. I might mention that one of the things that bothers me a lot is that the papers that I see are coming from outside of the United States. American research in this particular area is lagging. There are very few papers that I see that have that come out of the American universities today. That needs to change. And then I think education curriculum is a huge opportunity. I mentioned last week that I had a granddaughter who had a solid 4.0 in engineering, in fact, applied engineering from a major U.S. university. Never heard digital twin in her 4 years there. So the universities curriculum need to incorporate this, and they need to incorporate it from the freshman year on for two reasons. One is I think we weed out the potentially very good engineers by boring the hell out of them, and I think that they need to use the tools that they've been brought up with. So here are sort of selected publications that I've done over the years. I also have a YouTube channel that you can have access to with selected presentations, keynotes that I've given. And these are all available out on my ResearchGate website. And with that, I thank you for your attention. Hope I've kept you pretty interesting and maybe even a little scared about making sure that we address a lot of the issues that I've talked about. And with that, I will turn it back over to our host.
Thank you, Dr. Greaves, for that fascinating discourse. Excuse me. We have a few questions for you. The first one being, there are many definitions of digital twins since the one you originated. What is the implication of so many definitions? In other words, what are the negative effects from having so many definitions? And do you think it affects digital twin strategies and uses?
Yeah, so that's a good question. So as I said, I am not too concerned about the digital twin definitions. And one of the things I posted recently is, what's the difference between one company's digital twin definition and another? And the answer is a good marketing department. So the issue of it is that I think that the opportunity is to look at the model and look at the use cases. And I think that those fall out of what that is, as opposed to a specific word definition. From my perspective, word definitions evoke what you already know. I mean, They really, if you're, one of the examples I've shown is in the Middle Ages, the definition of an elephant, and the pictures that came off of that were very, very different than the actual elephants in Africa. And so I don't think you use definitions to build your understanding of things. You create your understanding, and the definition evokes it. So I'm not too concerned about it. And as I said, I don't even, I'm not even wild about my definition. But I think that what I do like is the model, and then the use cases that derive from that model.
Gotcha. Our next question. Digital twins concept practice exists for several decades. The past 5 to 7 years has seen an explosion of literature. Can you evaluate why is it the time to focus on it now, and what unique values can be brought by digital twin versus without digital twin?
So I think that the answer to that is the fact that I was pretty early in the curve in terms of the idea of the digital twin. It really couldn't be implemented. As I said, I worked I was involved with the first supercomputer. I mean, we didn't have enough capability. I mean, there is the myth that this started with the Apollo. There wasn't any digital capability in the Apollo era. I mean, I ran a mainframe operation, in fact, near Kennedy Space Center in Orlando. I had 192K of internal memory. You couldn't do any digital things with that. So it required that Moore's law come about. And I think that has sort of occurred by 2015, if you look at my graph, that basically then said, hey, this isn't science fiction. This is stuff that we can actually do. So it required getting the computing capability and storage and communications to be able to really start to take seriously the kind of capabilities that digital twins so promise.
Got you. Thank you for that. Our next question, how do you define interoperability, and what aspects of interoperability are unique to digital twins?
So I don't know that there's anything unique to digital twins. I think we always have the interoperability things when we move into the digital world. I mean, ERP systems, for example, have the same particular problem in terms of having different ERP systems and having interoperability. I mean, I think it requires the fact that you have, common remote calls and common attributes that allow you to basically be able to share information. I was involved in a project where in the early 2000s where we were looking at XML as the ability to do that. We just didn't have the computing capability to do that. Today, I think we do have the ability of having it, and there's some pretty good demos I'm seeing out there of operations that in essence start to gnaw away at the interoperability problem. So there's nothing unique about it. It's sort of the nature of the fact that you have, information granularity at the smallest level. Atoms enforce their own interoperability. Digital bits don't. And so we basically have to do that work on our own.
Gotcha. Our next question. Digital twins always exist before physical. What if we obtain an adversary device, reverse engineer it, and digital twin it to understand how it works or understand its vulnerabilities? Or digital twin a priceless historical antique like I'm not sure how to pronounce this, Antikythera mechanism?
Yeah, so I don't know what that word means, but we'll go for the rest of it. So I guess I need to clarify that the digital twin doesn't always exist before the physical version. I mean, we don't have a digital twin, the digital twin of the B-52 bomber. We can have a digital twin of it, but obviously that ship has sailed a long time ago. What I meant to is that the fact that when we're developing a product, we will have the digital twin of that before we have the physical product, assuming we're doing this right, okay? So for example, I've seen some really good implementations of digital twins in archaeology. I mean, Rome, for example, they're basically using digital twins as they go down level after level, and they have to destroy, the previous level before they can get to the next level. So they capture that in the digital twin. So yes, you can have a physical version before you have the digital twin version. So it isn't that you always have to have it. But if I'm developing a product, I obviously want to develop that in a digital twin first, where I can make all my mistakes virtually as opposed to physically. So good question, and I want to make clear that you don't always have to have a digital twin before you have a physical one. And certainly the example they used of getting a digital twin of some sort of adversarial product and then doing modeling simulation of it would be a great use of digital twin capability.
Thank you for that clarification. Our next question. Heard the assertion that a digital twin exists prior to a physical counterpart. Is the pre-physical digital twin a model? What happened to the word model in digital twin parlance? Thank you.
Yeah, so I addressed that in a recent EE Times article that's available if you go search it. But a model is this idea that says, gee, I have this phenomenon I want to take a look at. Okay, for example, I want to see what Navier-Stokes says about this particular shape. So we do have models, but as soon as we say, look, I'm just going to make a product out of this, or a physical entity that I'm thinking of, is when we have the digital twin. So we still have models as we're sort of experimenting with various phenomena, but as soon as we basically say, look, I have a project to build next generation airplane or this sort of pharmaceutical, I have a digital twin. So you can go look at my article that sort of describes why I think models and digital twins are different.
Thank you for that. Our next question, well, not a question, but a comment. Dr. Greaves makes a great point about our workforce competency to take advantage of digital twin concepts and advanced technology enabling it. There needs to be more emphasis on this. And our next question. I'm sorry.
My poor little granddaughter never heard about digital twins, and her 4 years of getting a 4.0 in a well-respected engineering school. And I actually took the dean to task on that, and he said, "Yeah, we're getting there." Well, they're not getting there fast enough. I mean, quite frankly, these students that are coming in have this natural understanding of the digital world, and this needs to get into our educational systems. And we do some things like FIRST Robotics and things like that. But the idea of working this stuff virtually, now again, it can't be black box. I want to make that point, is that they need to understand. But how many different Q problems do they need to do before they understand what a differential equation is? And anybody that drives a car understands differential equations. So I think that that the educational environment has to basically come to grips with, we really need to start doing something pretty dramatically in the near future. I am hearing about some educational institutions that are implementing this, but not enough. So I agree with the comment.
Thank you. The next question. Can you please one more time explain the difference of classical computational models and digital twins? Well,
I think that classical computational models, one of the things I said is we're looking at the idea of fusion of physics, which are classic computational models, if you will, and big data. So I think that they are an integral part of a digital twin in terms of predicting performance. So I mean, the two things that we sort of had in terms of the digital twin era was, first of all, the geometric representation. I mean, it was basically a shape in space that we had great fidelity about how things fit together. But the big opportunity is obviously, how does it behave in the physical environment? So I think that there is a huge need. I mean, we've got to have that computational capabilities of the physical world in order to be able to do that. But again, I would add that we also need to look at, what can we learn of big data? I mean, there's some claims that we can get to first principles by the data. I've seen pros and cons in that, but I think that is a research opportunity that the National Academy should be proposing. Is I think that is a huge opportunity in terms of getting better fidelity of our digital capabilities.
And the person who asked the question also provided a clarification. They said, I mean exact, distinct characteristics.
So I guess I don't understand necessarily what exact distinct characteristics are. I mean, from my perspective, is does it predict the physical world? And you know, there's a saying that, you know, all models are wrong, but some are useful. Well, you know, if it's wrong, I mean, in this particular case, we're trying to predict outcomes. If we don't get the outcomes, then I don't know what the model does for me other than maybe point me in a direction that I need to do new research for.
Gotcha. The next question, can we talk to considerations of the butterfly effect with digital twins? Can a digital twin truly simulate the real world? What is the fault tolerance and how to use IoT data collection to improve that tolerance?
Areas that I mentioned is, you know, uncertainty quantification. I mean, although I have a problem with that term, is that if it's uncertainty, I don't know how I'm quantifying it. But be that as it may, the idea of basically turning uncertainty into risk, I think, is a big opportunity. And I think that one of the issues in terms of complex systems. So I just did a panel for AIAA on complex systems. In fact, we have a group called CASE, Complex Aerospace Systems Exchange, is this idea that says that you know, one of the issues is weak signals are an example of something you need to take a look at. Humans tended to basically ignore that because they don't think it's important. Digital twins can focus in on that. So because they are so ability to be focused, they can look for weak signals, i.e. butterfly effects, if you will, that will allow us to pick up anomalies well before they occur. So I think there's great opportunities there. Again, you know, one of my perspectives is that it's going to give us probabilities, but those probabilities could increase as I see more and more weak signals that add up to it. So one of the characteristics of highly reliable complex systems is a focus on weak signals, and I think that digital twins have an opportunity to help us in that particular area.
Okay, and our last question for you. One issue in the academic—
Thanks.
I know. One issue in the academic realm is the investment. Educational institutions are slow to adopt use due to costs, especially state-run institutions. How can we encourage industry to move academia to adoption by infusing the currency to enable it?
A darn fine question, and I don't know whether it's investment, to be perfectly honest. I mean, my experience in this area is basically it's more about inertia and less about investment. And so I think that, and I've basically worked this since 2000 when I was on the I ran the business school board for Oakland University, is that industry has said, look, we can't afford the 2 years that we have to train and educate new graduates. And there is a reluctance. The inertia thing in academic institutions is, I think, much bigger problem than the investment.
Thank you, Dr. Greaves.